each combination of magnitude and distance, right? So let's start with 1. Okay, so combination 1. Combination 1. We've got a magnitude, or let's say a distance, equals 27.01. And we've got a magnitude, let's use the magnitude of 4.17. Okay, what we need to do for each combination, so that's combination 1. Each combination, we first calculate the peak ground acceleration. So we use our Gutenberg-Richter relationship. Okay, so we can calculate, we've got a relationship that's something like this, log peak horizontal acceleration equals blah, 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 blah. It's a function of, I don't know what it is, let's say, I don't know, whatever it may be, plus something, this equation here. Here. Okay. Nice. Ln. Okay, so Ln log normal. Okay. 6.74 plus 0.859 times m minus 1.8 times the log normal of r plus 25. So what we do is we put this into here and this into here, and we end up with our value, right? We end up with something, let's say, whatever that may be. Right. Some value, let's put x for the time being. Okay, so we do that for combination 1. Okay? Then what we do is we calculate the standard deviation. So what's standard deviation here? Not standard deviation. Standard deviation is 0.57. Okay. So then that's a constant in this case. So then we convert that to the standard normal curve, right? So when I say convert that to the standard normal curve, okay, so remember, okay, and what's the target acceleration we're interested in? The target acceleration equals 0.01 g. Okay, so remember for the standard normal curve, we have to calculate our z value, which equals the value minus the mean divided by the standard deviation. Okay, so that's the value that we want, that we're checking on, right? Okay, that's the value that we want to check if it's going to be exceeded. So this value here is a target acceleration. This value here is the mean. Okay, this is the mean value. And then this here is our standard deviation. So we get our z value. Okay. Now from our z value, we can calculate the probability of, it's a log normal, let's do it on a standard normal curve. So from our z value, we're going to end up with this. Something like that, right? Remember last week we talked about that? Okay, but what we're interested in is that target acceleration being exceeded. So we're interested in this here. Okay? So to get that probability, anyway, in the first instance, let's get that probability of the target acceleration, that. And we do that by going to our normal distribution curves. or we can do it using Excel, and we'll calculate this probability. Okay, let's call that probability. What do we call it? Probability of target acceleration. Okay? But then what we want is the exceedance. We want to find out how much, we want to find the probability of that being exceeded. So what's the probability of that being exceeded? Probability of exceedance for the target acceleration. Equals 1 minus the probability of the target acceleration. Oh, actually, in this case, it's like that. Yeah, okay, 1 minus that. Okay. And that will give us this here. That will give us this crosshatch here. Will give us that here. Okay. So this sounds complicated, but again, it's not really complicated. It's just basically we take that each combination of distance and magnitude. We calculate the horizontal acceleration, which is the mean horizontal acceleration. Okay, and then we want to calculate the probability. Given that mean acceleration, we want to calculate the probability of the target acceleration being exceeded for that distribution. So this actually, remember this formula calculates the distribution. Okay, so we've calculated the mean, okay, which is this value here, the mean. We've got the target acceleration, which is here. And we want to find out what the probability of that target acceleration being exceeded is, which is here, okay, on the standard normal curve. So, okay, so now, so here we've got it, okay, given that and that, for an target acceleration of that, that's the probability. And we want to find the probability of exceedance. And we repeat that what I've just done for all combinations. So for all combinations for source zone 1, all combinations of source zone 1. So what I mean by that, we go 27.04 for the distance, right? So we go 27.04. It's 27.04. Okay, that's combination 1. We'll do the same thing for combination 2, which will be 27.04, and the magnitude will be 4.5. We choose the next magnitude. And then we 27.04 with this magnitude and this magnitude and this magnitude, all 10 magnitudes. You need to calculate that. It's the same thing. Okay, for all combinations of M and R. Then what we do is, once we've done that, okay, we're going to end up with a table kind of looking like this. You're going to have your for your target acceleration, or particular target acceleration. So in this case it's 0.01. Okay, and then for each combination of distance and magnitude, okay, so we have 10 of these. Okay, we have 10 of these for each combination, so you've got 20. First combination is that 4.17, we've got 4.33, etc., all the way up to 7. You're going to end up with the probability of exceedance for this. Okay, so you're going to end up with the probability of exceedance. Okay, that's what that is. It's the probability of y exceeding that value given the magnitude and the distance. That's what that stands for. And then you want to multiply that value here, this probability of exceedance that you've calculated. You want to multiply that by, I'm going to rub this off now. Okay, but it's in the, I think I've uploaded that tutorial. Rub this off. So we calculated the probability of exceedance, right, for that target, given that combination. Okay, so whatever that is, let's say it's 0.2 or something. Then so these are our probabilities here. So that's the probability of exceedance. Then we have to multiply it by the probability that the distance occurs, and we get that from our distribution. And then multiply it by the probability that the magnitude, that this magnitude occurs. We get that from the distribution. So we go that times that times that. Okay. And then the last thing we multiply it by is the probability of an event occurring on that source. Okay. So remember that this source here, the source, there's a probability, and it'll be given to you in the problem statement of what's the probability of an event occurring at all. So multiply it by that, maybe it's 0.3 or something. So that times that times that times that, and then we get a value here. Okay, these are the probabilities. And our final probability, okay, which is this. Okay, that times that times that. Okay, maybe this one here you can multiply it right at the end. Okay, let's take this one out, multiply it right at the end. So that times that times that. Sorry, confusing everyone again. That times that times that equals this. Okay. Then what we need to do is we need to sum them. And sum all of them, all of those combinations. So we've got 10 of these for the target acceleration. Okay, whatever that is. Let's call it x. We sum all that, we get the total here. Okay. Then for how many sources, how many target accelerations we've got. No, sorry. Then what we do is for each source zone, we do the same thing. So source zone 1, source zone 2, source zone 3 for that target acceleration. We sum that as well. We add them together. And then finally we multiply it by this value here, which is the probability of an event occurring. And that's essentially what, and then we'll end up with 1 point. From that, we'll end up with 1 point here. And you do that whole process again for the next target acceleration, and the next target acceleration, etc. So that's why I say, if you use Excel, it can get unwieldy. Okay, so here's the example. Here, from that one, the first combination, we've got magnitude of 4.17, distance of 27, target acceleration 0.01. Okay. This is the probability that's going to be exceeded. This is the probability that it's of the magnitude of 4.17 occurring. That's from your distribution. This is the probability of the distance of 27. It's going to occur at 27 meters. And then we multiply it by, this probability of the event occurring itself, which means the probability of it being greater than 4. Okay. And then we end up with this. Okay. And that, we've got to do that for each of the combinations, add them all together, and then do the same for each source zone, add those together, and we end up with 1 point on our hazard curve. We do it for each of the others. And that's how we end up with the hazard curve. So for exceedance of target acceleration level, all combinations of magnitude and distance give an annual rates of exceedance as follows. And so we end up with something like this. magnitude, distance, we end up with a table like that. We repeat it for source zone 2 and 3. Okay, so for source zone 1, we sum all that up. That's for the first target acceleration. Source zone 2 and 3, we do the same. So the annual probability of exceedance at target acceleration of 0.01 g will be exceeded by earthquake is 2.994. So that's that plus that plus that. And that gives us 1 point on our hazard curve, which is here. So we've added that plus that plus that, we end up with that. And then we do the same thing for all the other target accelerations. We end up with this curve. Okay, now once we've got that curve, we can then solve some questions. So has anyone got any questions? I suppose you've got a lot of questions on how to come up with that curve, but I'll just bring you to the next part of the homework tutorial before we go back. So using that, once we've got the hazard curve, then we can answer these questions, okay? Using the Poisson distribution. And we've also got some questions here in the homework on how to calculate similar questions, but not on, remember the hazard curve is talking about acceleration, right? Acceleration. You're also using the Poisson distribution, what we did last week. Okay, remember we were calculating certain probabilities using the Poisson distribution. You can also use the Poisson distribution to calculate the size of the event on this using the Gutenberg-Richter recurrence law. Okay, so that's what these questions are about. But let's jump to here, the homework assignment. You don't have to do it, but what you might want to do it. It's